Hello, I'm Colin from We Learn to Share, and today's lecture is the last lecture about electronic structures and the periodic table. My last two lectures of this chapter were focused on quantum mechanics, but this lecture is less related to it, and it will be quite easy. We're going to start with atomic orbitals in this lecture. Each orbital containing an electron of an atom can be indicated by marking the region with certain probability of finding the electron. While the s orbitals are spherical and identical in all directions, other orbitals can have direction. These orbitals are expressed by indicating the variables that appear in the orbital's function. For example, the p orbital can have 3 directions, and each of them are written by px, py, and pz. Now, using these orbitals, we'll try to write down the electron configuration of an atom. Before doing this, we have to look on the Pauli exclusion principle. No two electrons in the same atom can have identical values of all 4 quantum numbers. In the electron configuration, the number of electrons in each sublevel is expressed. In this example, 1s2, 2s2, 2p5, we can see that there are 2 electrons in 1s and 2s sublevels, and 5 electrons in the 2p sublevel. To predict the electron configuration, we must know the order of sublevels getting filled. The orbitals fill in the order of lower energy level, and the general energy order of these orbitals can be simply found using this diagram. However, some exceptions can occur, and you will learn these and their explanations while studying further into quantum mechanics. In the case of elements with larger atomic numbers, it is complicated to write the whole electron configuration, so we often express them using the abbreviated electron configuration, starting with the preceding noble gas, followed by the configuration of extra electrons. For example, the electron configuration of sulfur can be simplified into this, and similarly, nickel can be simplified into this configuration in the table. Assumably, the atoms of elements in a group of the periodic table have the same distribution of electrons in the outermost principal energy level. Also, elements of certain groups can be classified depending on the orbital they fill. The elements of group 1 and 2 fill an s sublevel, and the elements of group 13 to 18 fill p sublevels. They are called the typical elements, and each of them differ greatly in characteristics because the number of valence electrons increase as the atomic number increases. The elements of group 3 to 12 fill the d orbitals, and they are called transition metals. These elements are hard to separate, since many of their characteristics are similar as the electrons that fill up the inner electron shell. The lanthanide and actinide, the group of the 14 elements that fill up the f orbital, are also hard to separate for the similar reason. If we go another step further into the electron configuration, we can draw the orbital diagram of an element. In this diagram, each orbital is represented by parentheses, and electrons are shown by arrows pointing up and down. The electrons filling in the orbital has 2 opposite spins, so if each parentheses are filled with 2 arrows of opposite directions, it means that the orbital is completely filled. In some levels with multiple orbitals, the following principle can be applied. The Hund's rule states that every orbital in a subshell must be occupied with 1 electron, each with the same direction of spin, before an orbital is occupied by 2 electrons. This is important in filling the orbitals such as p, d, and f. After drawing the orbital diagram, we can determine if the element is diamagnetic or paramagnetic. If unpaired electrons are present, the element is paramagnetic, and if all electrons are paired, the element is diamagnetic. These electronic structures can also be applied to monoatomic ions. When a monoatomic cation is formed from an atom, electrons are removed from some levels in the highest principal energy level. When a monoatomic anion is formed from an atom, electrons are added to unoccupy some levels with the lowest principal energy level. Elements close to a noble gas in the periodic table tend to form ions with the number of electrons of the noble gas, and therefore we can predict that their electron configurations follow that of the noble gas too. These ions with the same electron configuration are said to be isoelectronic. The transition metals do not form ions with noble gas configurations because the energy requirement is too high. When they form cations, transition metal atoms lose the outer s electrons first. This is an exception to the energy level order we discussed about, and it can also be explained in quantum mechanics. Next, we will talk about the periodic trend in the properties of atoms. Do not take this part too seriously, because countless exceptions occur in experimental values, and you will only get to understand them when you fully understand the advanced part of quantum mechanics. The atomic radius can be defined assuming a spherical atom and measuring half of the distance between the closest atoms in an elemental substance. The atomic radius increases as the period increases, since the number of valence shells increase. The atomic radius, however, decreases as the atomic number increases in a single period, because the amount of charge the added electron cancels is smaller than the amount of charge the added provides. This happens because many factors, such as the distance between the electron and the atomic nuclei, or the repulsion between electrons, make each electron only be able to feel the effective nuclear potential, the decreased value of the nucleus potential. The ionic radius can be predicted in a similar way too, and this is too obvious to mention, so if you cannot understand, just look at the book. Lastly, we will look on the quantities used to compare the tendencies of different atoms to gain electrons. To get to this, we will look first on electronegativity. This measures the ability of an atom to attract the electron pair to itself. Electronegativity ordinarily increases moving from left to right and decreases moving down a group. It can be calculated in terms of ionization energy and electron affinity, or in terms of bond energy. To mention the first method shortly, ionization energy, first ionization energy in particular, is the amount of energy needed for the removal of the outermost electron. The electron affinity, on the other hand, is the amount of energy released when an electron is added to the atom. These two quantities have the same periodic tendencies as the electronegativity, and their sum equals the electronegativity. This is the end of today's lecture and this big chapter. I tried to make the last lesson a lot easier than the primary two, so I hope it is easy for you to understand. Next time, we'll continue our journey onto the curriculum, so make sure you subscribe to the channel, leave a like, and turn on the notifications.